All right, so the next chapter in the Klein textbook is switching gears from mechanisms into spectroscopy. For those of you that were around for last quarter, we actually did IR spectroscopy in lab. We had a whole lab just working on IR spectroscopy. So rather than reteaching it, what I've done is I've created a supplemental lecture video for anybody that wants to review to go back and kind of brush up on IR spectroscopy. So in OneNote, what you'll see is kind of all the notes that correspond to the video, kind of describing the theory of IR spectroscopy, how to interpret IR spectra, kind of using the spring analogy that I used in lab, and then how to interpret IR spectra using some cheat sheets. So for example, this sheet down here, once it loads, is that IR chart that I have posted on the class website. Students have asked, will I give this to you on exams? The answer is yes, for Chem 262 only, meaning starting in Chem 263, no more cheat sheets. So this kind of gives you a rolling start into interpreting IR spectra. What I will say is the most common mistake that students make with IR is they look at their IR spectrum and they try to find every single peak and correspond every single peak to what's on this chart. That's a really bad way to go about it, right? Instead, what I do is I try to approximate in my mind where the peak should be and then use this in any situations where I'm a little uncertain. Why is this a simplified chart and not absolute? Does anybody remember what shifts peaks around? What do you think? Resonance. Resonance can shift peaks from these ideal values, oftentimes up to 30 or 50 wave numbers to the right. So these aren't absolute. Don't treat them as absolute values. There's some IR practice problems. I actually just pulled these ones from the book, but walked you through a few examples in the lecture video. So if you do need help doing that, make sure you do that. The skill builders for this chapter will be due on Tuesday. I realize there's a lot of them in this chapter. So what I will say is if there's a problem where it says, all right, do problems A through Z for 12.2 or whatever, do as many as you need to do to feel comfortable. Really, the skill builders are about you practicing for yourself, not you practicing for me. So do as many as you need to do to feel comfortable with IR. Does that sound fair? All right. So what we're going to do today is we're going to talk about something new. We're going to talk about mass spectrometry, which is kind of cool. All right. Has anybody ever heard of mass spectrometry? A few people? All right, so it's often kind of featured in a lot of the CSI shows. However, it's not as fancy as the CSI shows make it out to be. Oftentimes they, on CSI, will say, oh, we've got the sample. We know that it was from, I don't know, a Ford pickup truck built in 1962, blah, 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 blah. It's not that good, but it does give you a lot of information about a potential unknown compound. And so let's kind of take a look at the simplified view of how it works. So let's say we've got, sorry, let me change the thickness here. Let's say we've got some sort of organic compound, and we know organic compounds tend to have carbon-carbon bonds within them. And what we're going to do is we're going to blast this organic compound with an electron beam. So if you do that, the electron beam will hit one of these bonds. And let's take this carbon-carbon bond. This covalent bond has 2 electrons in it, right? So if we hit these electrons in that covalent bond with an electron beam, we can actually knock one of those electrons out. So what ends up happening is you'll have one electron that's lost. And so I'm just going to show that kind of on the outside as E minus. What does that tell you about this portion right here? Does it have a charge? Yeah, definitely. It lost an electron. Oops. Let me change this. So this has a positive charge. So what this is called is a radical because it has an unpaired electron, but it's also positively charged. So this is going to be our radical cation. Mass spec can actually observe these radical cations, and we'll talk about why they observe radical cations and not neutral molecules here in a second. All right, and then at this point, we know it's really, really unstable in this radical cation phase because that electron essentially has to pick a carbon to reside on, right? So what we could say is, well, maybe it's going to hop over to that carbon, which means the left carbon is going to be without an electron, means it will have a positive charge. And then over here, the right carbon will be a radical. So the radical cation will ultimately split into two fragments. One's going to be our cation, and the other one's going to be our radical. So the important thing to remember is that mass spec can only see things with charges. So it can be used to observe molecules or fragments with charge. So it could either be a cation or an anion. You'll notice in the Klein textbook, though, that he almost exclusively shows cations. However, you can actually switch the mode of mass specs to observe either cationic or anionic fragments, depending on the mass spec that you're using. So it's kind of neat. So then the question is, well, why can we observe cations and anions, but why not radicals? Well, radicals we know don't necessarily have a charge associated with them, right? So let's kind of dive into the theory behind this. So here's what a simplified mass spectrometer looks like. So we're going to start over on this end. And what we're going to do is we're going to inject our sample into an open end of your mass spectrometer, typically using a syringe. And then the next portion that we're going to hit is this heating coil. When your sample hits that heating coil, it will be vaporized, right? Because when we heat things up, we create a small amount of vapor or even a lot amount of vapor, depending on how volatile it is. And then that vapor is going to be fed through an electron beam. That electron beam will again kick out one of those electrons in the covalent bond, and then your sample will get accelerated through your mass spectrometer using a series of magnets. And then once it's ionized, it'll actually go through a magnetic field. And let's take a look at why this magnetic field works. So let's say I've got my positive charge, right? I'm just going to simplify that as a positive charge with a circle around it. And it's going through your mass spectrometer like this. And then all of a sudden, you've got these magnets above and below. And let's say this magnet up here is your positive pole. And down here, this is your negative pole of your magnet. What do you think is going to happen to that positive charge as it's getting flung through? It's going to gravitate towards the negative side, right? Because opposite charges attract. So what will happen is this will start to arc kind of down. That's kind of exaggerated, but you get the idea. And it's going to go over here, and it's going to hit this detector. So I'm just going to call this the detector. And really what we're going to do is we're going to measure the deviation from a normal straight line to when it hits the detector. So we're going to be measuring kind of this distance of deflection. What do you think impacts the distance of deflection, meaning how far the cation arcs? How big the charge is? Absolutely. So if you have one positive charge versus two positive charges, that's going to change it, right? What else could impact that? Mass, right? Typically lighter things are easier to deflect than heavier things. So that's exactly what we're going to look at in mass spectrometry, is we're going to look at both charge and mass. Oftentimes what that's referred to is the M to Z ratio, because it's not looking at one or the other, it's actually looking at both, right? So let's take a look at a sample spectrum. So down here, we've got this. M to Z is your charge, or sorry, mass to charge ratio. Usually this is just going to be the same as your mass. Does anybody know why? Yeah, because normally we're dealing with +1 charges. The reason for that is it's simply a lot harder to get a +2 charge. Doesn't mean it never happens, it just means it's less common. So for all intents and purposes in sophomore level organic chemistry, we're going to assume that the mass to charge ratio is just going to be the mass, because most of the time the charge is going to be equal to 1. Does that make sense? So let's make a note. So usually charge equals +1. Therefore, m to z equals mass. Does that make sense? All right. And then on the right-hand side, we've got relative height. So this tells you some more information. If we zoom into the mass spec, we can kind of see a series of peaks in there, right? Not all of the peaks are of equal heights. Does anybody know why we're getting multiple peaks? There's actually a few answers to this one. Think back to Gen Chem. Isotopes, right? Is all carbon carbon-12? No, we've got some carbon-13. We even have a trace amount of carbon-14. Is all hydrogen 1 neutron and 1 proton? No. Sometimes we have isotopes of hydrogen too. So that can lead to a series of peaks like that due to isotopic distribution. The other reality is we might have dislodged one of the hydrogens in here too, right? So when we hit it with the electron beam, there's a fair chance that we actually pop off one of those hydrogen atoms, and what we're observing is the leftover cation. And so we'll talk more about that later. Does that make sense? I know this gets kind of abstract, and I apologize. I know it's hard to take notes with a lot of these graphs. So if you need to, just go back into OneNote, and you can even print off these notes if you'd like. All right. So now let's go into the next part. We're going to start looking at these peaks in a lot more detail. So what we have over here is something called a base peak. Oftentimes the base peak is going to be the tallest peak in the rightmost cluster. So over here, this is going to be our base peak. Oop. And the way I normally do this is I say it's the tallest peak, not necessarily overall, but in the rightmost cluster. And what this is referred to, and you'll see this a lot in the book, is this is your, parent peak. So do you remember on the last page where I said if you hit a molecule with electrons, it will knock out one of those electrons, and for a brief period in time, you'll see the original molecule that's a radical cation? That's what we're observing here. So this is our radical cation. All right, so that peak's really useful. And then down here, you might notice that we've got an additional peak. Ah, that's not a good color. I'll just do this one. We've got an additional peak that's 1 higher in terms of its mass to charge ratio. What do you think that's due to? Because normally if I look at CH4, this molecule that we're injecting in right here, what should the molecular weight be? We've got 1 carbon, carbon's normally 12. We've got 4 hydrogens, hydrogens are normally 1. So normally it's 16, right? Why are we getting a peak at 17? Does anybody know? Not resonance. So let's make a note. This is a peak that appears 1 mass unit higher. So what we call this is our mass plus 1 radical cation peak. Does anybody have an idea for why we might have this? Give you a hint, we just talked about it. Isotopes, right? not all carbon is carbon-12, right? So over here, this is due to our carbon-13 isotope. Does anybody know how much carbon-13 is naturally abundant on our planet, at least? Well, let's take a look at the base peak here versus our mass plus 1 peak. About 1%, right? So in this case, it's a really, really small amount that's due to that heavier isotope, but it's still a percentage that we do need to pay attention to. In fact, it's a really useful tool that we'll be able to use later. All right, so let's go ahead and take a look at a more complicated one. So what's this molecule that we're looking at now? Pentane. Hopefully we can all name that at this point in the year. All right, so we've got pentane there. Let's go ahead and identify our radical cation peak, meaning our parent peak. Where would that be? Try to identify the number. So over here, I would definitely say that that's the tallest peak. Is that always going to be our parent peak, though? No. It's the tallest one on the furthest to the right, right? So I would say this is the rightmost cluster, right? Okay, so now we need to identify the parent peak within that cluster. It's going to be the tallest peak, right? So this must be the parent peak right here. So I'm going to make a note that over here, this is going to be our parent peak. Sometimes you call this the parent ion. And like I said, normally this is going to correlate to the mass of your molecule because the charge is usually +1 in this case. So that's pretty useful. All right, now if we're looking at this mass spec versus the one that we were looking at before, things are getting more complicated. If you notice, we've got a cluster peaks here, cluster peaks here, cluster peaks here, and a cluster peaks here. What do you think these correspond to? Yeah, if we think about it, right, when we hit the molecule with electrons, we said we originally create a parent ion that's a radical cation, but then it fragments into a radical and a cation separately, right? So we actually broke that bond like we talked about on the last slide. So in this case, what do you think this peak over here is going to be? I would say it's likely that we lost a carbon, right? So if we look at this, this would correspond to loss of a CH3 radical, right? So really what that means is imagine losing that chunk off of the end of the molecule, right? We can actually observe this remaining chunk over here that would be the cation, where this side over here would be our radical that was lost. Does that make sense? So when we hit it, we're actually going to break it apart. All right, now let's think about the next one. What do we think this one corresponds to? Loss of 2 carbons. Specifically, it's going to be loss of an ethyl radical, right? So what we're going to do here is we're going to lose this chunk. That's going to be the radical that was lost. And what we're going to observe left over is going to be this 3-carbon cation right there. Make sense? All right, so this trend is going to be the same down here. What is this one going to be? Loss of 3 carbons. And then over here, this will be loss of 4 carbons. All right, so if we think about it, what we're really observing here is over here, this is going to be the cation. Let me clean this up. That's going to be our methyl cation. Over here, this is going to be the ethyl cation, right? Yeah.
The first one, would we have 4 hydrogens, or would it be?
Or sorry, it should be 3. Thank you. Good catch. And then over here, be 3 carbon cation, and then last but not least, that would be our 4 carbon cation. It's really, really important to remember, though, that what we're observing here is only going to be these cationic chunks. We can infer that we lost those radicals, but we can't see those radicals. Why can't we see the radicals? Because they don't have charge, right? We can only see things that we can deflect, assuming that they have charge, right? All right, so these do get a little bit tricky. Do I have, oh man. Thank you. That's embarrassing. I know. All right. So moving on, I'll show you some useful tips. Because it is really overwhelming looking at this forest of peaks. Oftentimes when you're looking at it, it's just completely overwhelming. You don't know where to start. So I always start by looking at my parent peak. So if the charge is +1, then this tells you the molecular mass. So that's pretty useful, right? Just identifying some unknown compound's molecular mass can be very helpful when identifying that molecule. There's another trick you can do too. So let's take the molecule above. What was the molar mass for this molecule? So we've got 5 carbons, that'd be 60, right? And then over here we've got 3, 6, so that'd be 66 plus 2, 4, 6, be 72, right? Some students will ask, well, why don't we add in all the decimals? Does anybody know why? Well, let's take a look at the decimals on the periodic table, right? Do those decimals mean that the atoms always weigh that amount? Why not? It's an average of all the isotopes, right? So this is a best case scenario for atoms that are all of the most abundant isotope, right? So we're essentially just going to round, if that makes sense. All right, so we've got that one. Let's do another one. This one's a little bit different. We're going to throw in a nitrogen. So this is an amine. This has a molar mass of 73, if you do the math there. All right, let's do another one. And this is going to be 74. So we can go ahead and add up all these atoms and predict where their parent ion will appear on mass spec. This might not seem very useful at first glance, but I'll show you the useful trick. Is that molecules with an odd number of nitrogens also have an odd mass number. So this is kind of helpful, right? Because if we look over here, this is even. That tells us that we have 0 nitrogens, which is an even number. Over here, we've got odd, meaning we've got an odd number of nitrogens. Over here, even. So it doesn't really look that useful, but really if you ever see an odd number for your parent ion, that screams nitrogen at you. It's a huge clue that you've got a nitrogen atom somewhere in your unknown molecule. Does that make sense? So most compounds have an even molecular weight, assuming that they don't have an odd number of nitrogens. Yep. Yep. Yeah, what would happen if we had 3 nitrogens? It'd be odd again. So we can use that simple rule to kind of give us clues as to how many nitrogens we have in an unknown compound. All right, so now let's jump into the next part. It's kind of fun. Analyzing that M+1 peak. What was the M+1 peak for again? Isotopes, right? Let me clean this up. So it's due to a heavy isotope, specifically an isotope that has one extra neutron. It's usually not super abundant, but there's a probability that we have them. So let's take a look at the common elements in organic chemistry. So we've got carbon. Carbon-12 is far and away the most abundant form of carbon. It's 98.9% of all carbon on Earth. So nearly all the carbon inside of our body is carbon-12. However, like we said, carbon-13 is actually present at 1.1%. It's a really, really small amount, but it's still something we need to pay attention to. All right, carbon-14 is a trace amount. Does anybody know what we use carbon-14 for? Yeah, radiocarbon dating. So if you ever hear like this fossil is 65 million years old, the reason they can tell that is due to radiocarbon dating looking at carbon-14. So it's a really useful one for that, not so much in mass spectrometry because it's such a small amount, our detectors aren't capable of even picking it up very well. All right, what's another element we could look at besides carbon? Yeah, we could look at oxygen. So oxygen-16 is 99.96% oxygen-16. There is some oxygen-17 on Earth, but it's 0.01%. Really, this is so small, it's hard to detect. So at least the practice problems in our book, we're not going to be worried about heavy oxygen. You really only use heavy oxygen if you have a very, very expensive mass spectrometer that can go out to multiple decimal points. But for right now, we're not going to worry about this. All right, what's another element we could look at? Hydrogen. All right, so we've got two different types of hydrogen. This one's also 99.96, and this one's also 0.01%. So again, I'm going to say that this is so tiny that it's hard to detect using at least most standard equipment. The one we do need to worry about is this one right here. Because 1.1% is a heck of a lot bigger than 0.01%. So we can see this. All right, so I'll show you a cool trick. And this involves some math, because everybody loves math. So let's say we've got some sort of unknown sample that we're injecting into our mass spectrometer, and we want to figure out how many carbons are in that sample. We can actually use the C13 isotope as a clue. So I'll show you the formula. We can find the number of carbons by taking the mass plus 1 peak, specifically its intensity. What do I mean by intensity? It's how tall it is, right? So how high up it goes in that spectrum. You take that and you divide that by your parent peak, which is right next to it, right? Immediately to the left. So you take this, essentially that's your ratio of your C13 peak or your mass plus 1 peak divided by your parent peak, right? So really what we're looking at here is just the ratio of the heights, right? The heights are kind of arbitrary. We could set them to be whatever we want, but the ratio will be absolute. Does that make sense? Okay, so we're going to take this ratio and we're going to multiply this by 100%. So really what this is saying is, compared to your parent peak, how tall is your mass plus 1 peak? Is it 25% as tall? Is it 10% as tall? What size is it relative to your parent peak? All right, and then what we're going to do is we're going to divide that by the natural abundance of carbon-13, which is what? Percentage-wise? 1.1%. Right, so it says normally for one carbon-13 atom to exist, it's 1.1% probability. All right, so this is pretty useful. I'll show you some examples with this. So this sample that we're looking at has a mass to charge ratio of 68 with a relative, oh, sorry. Let me add this in. Everyone's angry now. Let's keep it consistent. And a relative intensity of 100%. Again, the relative intensity, you can scale it to be whatever you want. All right. The mass plus 1 peak, meaning the mass plus 1 radical cation, has a mass to charge ratio of what? It's got to be 69, right? So it just makes sense that it's one heavier by definition. And a relative intensity of 4.3%. How many carbons? All right, so let's go ahead and plug this into the equation. So it's going to be 4.3 divided by 100 times 100. We're going to divide this by 1.1. Hopefully we don't need calculators because we're just going to roughly guesstimate, right? So let's do quick math, right? Hundreds are going to cancel out there, so it's 4.3 divided by 1.1. It's about 4, right? So in this case, it's not going to be perfect math, but it's going to be good enough for an organic chemist. So about 4 carbons. So that gives us a really good jumping off point for further investigating this unknown compound. Yep?
So we always run it off.
Yeah, so the question is, do you round up, do you round down? What do you do if you're at, let's say, 4.5? Sometimes it's not always clear. Sometimes what you do is you say it's either going to be 4 or it's either going to be 5, and you have to look at other clues to kind of go with it. Mass spec can be useful. It can be a little bit deceiving. What I always tell students with spectroscopy is like going to court. When you go to court, your job is to prove something beyond a reasonable doubt, right? Does that mean absolutely prove something using a mathematical proof? No, it means just provide a lot of evidence to support your case, right? So as a scientist, we would just want to have overwhelming evidence. Does it mean that all the evidence will be in perfect alignment? Not always. Sometimes you got kind of gray area evidence where it's hard to tell. But for right now, we're just going to approximate as best we can. Make sense? Do you want to do another practice one with this, or do you feel kind of confident? Raise your hand if you want more practice for this one. All right, let's do one more. I'm going to mix it up on this one. So this one I'm going to simplify and not write a story problem. So mass plus charge, parent ions at 96, relative intensity of 19.0%. The mass plus 1 radical cation is obviously going to be at a mass plus charge of 97 because it's one heavier, and it's going to have a relative intensity of 1.5%. How many carbons in here? It's okay if you need your calculator for this one. Okay, so let's check this out. Mass plus 1, we said is 1.5 for its intensity. We're going to divide that by our parent peak, which is 19.0. Multiply this by 100, divide it by 1.1. Yeah, I'd say about 7 carbons. Make sense? All right, so now let's go into the fun stuff. Let's go to this one. In fact, I just pulled a skill builder from the book because I like it. So this one says, using the relative abundance of the mass plus 1 radical cation peak, propose a molecular formula. So let's go in and really zoom in on this. Let's first identify our parent peak on the mass spec, right? So this is the rightmost cluster. That means that this must be our parent ion. And then down here, that orange dot must be our mass plus 1 peak, so super duper tiny. Oftentimes on mass specs, though, you get printouts that show the relative intensity. So over here, we've got the relative intensity data for the various peaks because it's really, really hard to measure using a ruler or something that's a tiny little peak like that. All right, so let's determine the number of carbons here. So I'm seeing a few people holding up fingers. So let's check, right? So we know that this, by definition, is going to be our parent ion, and then this is going to be our mass plus 1 peak. So what I would do is I'd say, all right, it's going to be 1.2 divided by 20.9 times 100 divided by 1.1. I'd say this is about 5 carbons. All right, so that's a pretty useful tool. What do 5 carbons weigh? Whoops, 60? Okay, so 5 carbons has a mass of 60. That means that we've accounted for 60 of our mass units here. What's left over then? I'd say 26 mass units left over, right? Because if we think about our parent peak, it was 86. Of 26, right? Because we can assume that it's 86 minus 60 equals 26, right? Did you have a question, Awesome? For this part right here, is it 1.1, 1.2? Yeah, that's a good question. So the question was, where did this 1.2 come from right here? Who can help me with that? It's going to be this relative intensity, right? So it's the relative intensity of our mass plus 1 peak. Yeah, good question. All right, so we've got to account for the leftover mass of 26. All right, So we've got some clues that we've already identified. Does anybody have some other clues that we can look for that we've talked about? Some tips and tricks we can apply? The odd number, right? All right, so if we look at our parent ion, we said that it's 86. What do we think about our nitrogens? It's either 2 or none. All right, let's try to put our brains together. How many of you think there are 2? How many of you think there are none? Who can explain why they don't think there are 2? What do you think?
2 nitrogens would be 28.
Yep, if we had 2 nitrogens, they would be 28. We can't have 28. We only have 26 left over. All right, so other clue. Is number of nitrogens must be even since our parent ion is even and it cannot be 2 because we only have 26 mass units left over. Therefore, must have no nitrogens. All right, so that makes sense. So we've already figured out number of carbons. We've already figured out number of nitrogens has to be 0. All right, so let's try to figure out what else could likely be in an organic molecule. What other elements might show up in an organic molecule? Oxygen or hydrogen, right? Those are the most common ones we're running into. Which one do we want to try first? Let's try hydrogen. All right, would it be possible to have 5 carbons with 26 hydrogens on them? What do you think? It would be impossible to have 26 hydrogens on 5 carbons. Unless you made some super duper extra large Texas carbons that would make me incredibly sad, it is not going to occur. All right, which implies what? We probably have an oxygen. So let's make a note here, 3 in our thought process. Cannot have 26 hydrogens. So there is likely an oxygen. All right, so let's try to do the math here, right? So 26, this was our leftover. After step 1. All right, let's assume that we have 2 oxygens. Do you think that's possible? No, because that would be 32, right? We don't have enough. All right, what would 1 oxygen weigh? 16. So let's just say assume 1 oxygen. All right, that tells us that we would have 10 left over. What do you think this 10 could be? Hydrogen. All right, so let's do our best to kind of figure out the molecular formula. All right, we know it must be C5H10O, right? That seems to make sense given all of the data that we have in our mass spec. All right, let's see if we can determine some possible fits for this. Does anybody have some ideas? See if you can pencil down a few different isomers that would fit this molecular formula. I'm going to show you a trick too. Hydrogen deficiency hopefully I can spell this right. Index equals the number of pi bonds plus the number of rings. And the HDI, the hydrogen deficiency index, is a pretty simple formula. It's 1/2 times twice the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus the number of halogens, which I'll call X. So in this case, the HDI is going to be 1/2 2 times 5, right? Because we've got 5 carbons, plus 2 plus no nitrogens minus 10 hydrogens minus 0. So what would the HDI be here? So the 2 times 5 would be 10, plus 2 would be 12, minus 10 would be 2. We're going to multiply the whole thing by half. It must be 1, right? So this tells us it must have 1 ring or 1 pi bond. So this kind of helps us out when we're problem solving, right? So let's try to come up with some molecular formulas, or sorry, some structures that might fit C5H10O. Well, let's just do the easy ones first. So 1, 2, 3, 4, 5. We've got 5 carbons. We must have a oxygen somewhere, and we must have a double bond. So maybe it's like this. That would work, right? Or what if I put the double bond in a different position? Like that. Or what if I put my double bond there? Right? These are all isomers that would fit that molecular formula. And in this case, they all have 1 double bond in them, right? Or we could have something that looks kind of tricky. Maybe it's not straight chained. Maybe it looks like this. Or maybe we have a ring. We can go through and we can draw all of the probabilities of these molecules out, and then how would we go about narrowing these down even further? Maybe we use IR, right? So for example, if we do IR, how could we differentiate this molecule from that molecule? Yeah, aldehyde versus ketones. The CO double bonds will show up at different frequencies, right? How could we differentiate between these two? Well, I'd say the bottom one's not aromatic, right? We don't have alternating double bonds around the ring. We don't have a CO double bond, right? So we wouldn't have a peak at 1700. So like I said, I always treat it like a court of law. We can't always just go in with the mass spec and say, all right, we've won the case. Oftentimes you need mass spec, you need IR, and then we'll learn about NMR later on. We have to use as much evidence as possible to present our case, because sometimes, like you've seen with IR can be confusing. Sometimes mass spec can be confusing, but together they're less confusing. So we can use them as additive tools for deduction. Yep?
So how do we know that there's no halogens in it?
That's a good point. So how do we know that there's no halogens? The lightest halogen is fluorine, which is 19 mass units. We only had 10 mass units left over, so we can assume that there's no halogens in there. Good question. All right, so that's where we're going to stop today. I'll post the video for the IR review, and then your pod is just IR practice. So try to go through that IR practice and make sure you know how to solve IR problems.